It begins with a question that most of us never pause to ask. What is cold? We feel it, describe it, complain about it, but what exactly is it? Is it a substance, a force, or just a figment of our imagination? To most people, cold seems as real as the air we breathe. You step outside in winter and your teeth chatter. You grab an ice cube and your fingers sting. You bundle yourself in a coat, thinking you are shielding yourself from an invisible invader. Richard Feynman, the legendary physicist known for his playful wit and uncompromising clarity, had a shocking answer. Cold does not exist. This assertion is not a poetic metaphor. It is a literal, scientific truth. Cold is not a thing. It is not a particle. It is not a fluid. It does not flow. There is no cold energy that can invade you. There is only heat and the lack thereof. What we perceive as cold is merely the absence of heat, a condition in which energy leaves an object or a body, rather than enters it. To understand this, we must first understand what heat actually is. Heat is energy, not metaphorical energy, not the mystical warmth of a summer day. It is the kinetic energy of particles. Atoms and molecules are in constant motion. When something is hot, its atoms vibrate, spin, and collide rapidly. The faster the motion, the higher the energy. The more energy a system has, the higher its temperature. Conversely, when energy decreases, particle motion slows down. This slowdown is what we interpret as cold. Feynman would often illustrate this point with a simple example. He would hold an ice cube and ask, "Do you feel anything coming from the ice into your hand?" Most people would instinctively answer yes. After all, it feels cold. But the truth is counterintuitive. Nothing is coming into your hand. The sensation of cold arises because heat is leaving your hand and transferring into the ice. The ice is not sending anything toward you. There is no invisible cold particle invading your skin. This is a subtle but profound shift in perspective. From childhood, we are conditioned to think of cold as an active force. When we say, "It's freezing," we speak as though cold is something attacking us. Feynman insists that this is fundamentally mistaken. Cold is a description of energy flow, not an entity. It is reactive, not proactive. Let's break it down further. Temperature is a measure of energy. When two objects interact, energy always moves from the object with higher energy to the object with lower energy. If your body is warmer than the ice in your hand, energy flows out of your hand into the ice. That outflow of energy is what creates the sensation we call cold. The energy doesn't stop there. It melts the ice, warms the surrounding air, or dissipates into another system. The key is that cold is never an intruding agent. It is always the retreat of heat. To make this idea tangible, consider the sensation of stepping onto snow with bare feet. Your feet feel the cold immediately. But if you were to analyze the situation scientifically, you'd see that your feet are simply losing energy to the snow. The snow itself is not sending coldness into your body. If you were a particle-level observer, you would see vibrations slowing, atoms colliding less energetically, and energy being siphoned from your warmer body to the colder environment. Cold, in this sense, is simply what happens when energy departs, leaving less in its wake. Feynman loved to challenge everyday intuitions like this. He had a knack for peeling back the layers of human perception to reveal the underlying physical reality. One of his favorite demonstrations involved simply placing a hand near ice or immersing it in cold water. He would then ask, "Do you feel anything coming in?" People would inevitably point to the tingling sensation, the chill, but it was all the result of energy leaving. Cold is not tangible. Cold cannot be measured directly. Instruments detect temperature, which is always a measure of motion, never the absence of it. This understanding does more than clarify a common misconception. It reframes how we experience the world. Think about winter frost and snow. We see frost coating the ground in the early morning. We shiver and tighten our jackets. Our language describes the environment as cold. But in reality, the universe is only ever full of energy. Particles are moving, vibrating, radiating. The snow is not doing anything cold to us. We are simply transferring our energy into the environment faster than we can replenish it. Cold is a human-centric interpretation of an energy deficit. Even at a molecular level, the concept holds. Heat is the sum of countless tiny motions, vibrations of atoms in a lattice, rotations of molecules, the random jostling of particles in a fluid. Lower temperatures correspond to slower movement. Absolute zero, the theoretical minimum of temperature, represents the limit at which motion is minimized. But quantum mechanics complicates things further. Particles never stop moving entirely, even at absolute zero, due to what physicists call zero-point energy. There is no cold energy to extract, only varying degrees of motion and the absence thereof. Consider the implications of this idea for our daily lives. When you feel cold in winter, it is a signal your body is losing energy to the surroundings. When you warm yourself by a fire, a blanket, or clothing, you are not combating cold as an intruder. You are replenishing your energy to slow the outflow. Your actions are about maintaining heat, not fighting cold. Feynman also pointed out that many myths about cold are simply misunderstandings of energy transfer. For example, people often believe that touching metal in a cold room is more painful than touching wood. Why? Metal conducts heat better. When your hand touches metal, heat leaves your hand faster than it does when you touch wood. The sensation is sharper, the chill more intense. But again, it is not metal giving you cold. It is your heat leaving quickly. Even the expression cold weather is scientifically misleading. The air itself is a collection of moving molecules. In a room at zero KeC, air molecules are still in motion. They are not inherently cold. They simply contain less energy than your body. The chill you feel is your body energy moving into the air. Cold in every sense is an absence. The withdrawal, never a presence. Feynman would often take this principle further into thought experiments. Suppose you are floating in space, far from any star. There is no medium, no wind, no atmosphere. Do you feel cold? You might think so, but only because your body radiates energy away. Even in the void, cold is not attacking you. It is your heat leaving the system that produces the sensation. This realization is humbling. It forces us to confront how much of our sensory experience is constructed, interpreted, and often misattributed. Cold, like pain, like taste, like color, exists not as an independent entity, but as a signal, a way of understanding our interaction with energy in the universe. In a world obsessed with labels and absolutes, Feynman's insight cuts through the noise. Cold is nothing. Heat is everything. The chill you feel is not a substance invading your senses. It is the retreat of energy, a story told in motion and absence. To live comfortably, you do not seek to escape cold, you seek to manage heat. To survive in winter, you do not combat cold, you conserve and replenish energy. And this is only the beginning. In the next section, we will explore Feynman's experiments, demonstrations, and thought exercises that make this abstract idea concrete. We will see how centuries of misunderstanding about cold have led to myths, fears, and misconceptions. We will journey from the tactile experience of an ice cube to the quantum movements of atoms and molecules, proving beyond doubt that cold as we imagine it does not exist. Heat, motion, and the science behind the illusion. The first part of our journey revealed a shocking truth. Does not exist. It is not a substance, it is not a force, and it is certainly not an invader. Cold is simply the absence of heat energy leaving a system, whether it is your hand, your body, or the environment around you. But this insight, while revolutionary, is only the beginning. To fully grasp why cold is an illusion, we need to dive deeper into the physics that govern energy, motion, and temperature. Richard Feynman, with his characteristic clarity and curiosity, often explained these ideas through thought experiments and real-world demonstrations that are as simple as they are profound. At the molecular level, everything is in motion. The air around us, the objects we touch, even the water in a glass. Each is composed of atoms and molecules vibrating, rotating, and colliding. Heat is simply the measure of that motion. A hot cup of coffee contains rapidly moving molecules. A frozen pond contains slower moving molecules. The difference between them is not an addition of cold energy into the pond. It is a subtraction of energy from the coffee. Feynman would often illustrate this principle with a hand in ice demonstration. Place your hand in a container of ice water and feel the chill. The sensation is immediate and undeniable. But what is happening at the molecular level? Each molecule in your skin is vibrating, carrying kinetic energy. When your hand touches the ice water, these vibrations transfer into the water molecules. Your energy leaves your hand, slows down, and the motion of your molecules decreases. You feel cold because energy is leaving, not because anything is entering. He emphasized that this is not a metaphor. It is a literal truth dictated by the laws of thermodynamics. Energy flows from high to low. There is no opposite flow of cold. If there were, we would have instruments to measure it, and a completely different set of physical laws would govern the universe. But no such energy exists. Only heat exists. Only motion exists. Cold is merely a description of absence. To further clarify this, Feynman often used the example of metal versus wood. Place a metal spoon and a wooden spoon in the freezer, touch them both. The metal feels colder. Why? Both are at the same temperature. The sensation arises because metal is a much better conductor of heat than wood. It pulls energy from your hand faster. Again, nothing cold is coming into your hand. Your heat is leaving more quickly, and your nervous system interprets the rapid energy loss as a stronger sensation of cold. Feynman didn't stop at the macroscopic level. He took the idea down to molecules, atoms, and even subatomic particles. Consider the concept of temperature. It is a statistical measure of particle motion. The more energetic the particles, the higher the temperature. The less energetic, the lower the temperature. But low temperature does not mean coldness as a thing. It is simply less motion. Even at absolute zero, particles are not completely still. Quantum mechanics guarantees zero-point energy, a residual motion that can never be fully removed. Absolute cold is impossible. Cold does not exist even in the extreme. This principle also explains why space feels cold, or why it doesn't. In the vacuum of space, there is no air, no medium to conduct heat away. A human body exposed to space would not freeze instantly. The body would radiate energy away slowly, losing heat to the surrounding vacuum. Again, it is not cold invading. It is heat departing. Cold is an interpretation of energy deficit, not a tangible entity. Feynman loved to push these ideas with thought experiments. One involved a hypothetical cold beam directed at a person. If cold were a substance, you could aim it, deliver it, and measure it. But all experiments show the opposite. Energy always flows from warmer to colder objects. There is no beam of cold. There is only a beam of energy leaving an object, which our senses perceive as cold. Even everyday life provides examples of this truth. Consider air conditioning. It feels like the air itself is cold, seeping into your body. But the AC unit works by removing heat from the room, lowering the energy of air molecules. When the cool air hits your skin, it carries less energy than your body. Heat flows from you into the air. That's why you feel a chill. Cold is a convenient shorthand for the sensation, but it does not exist independently. Another striking illustration comes from extreme environments. In Antarctica or the Arctic, people endure temperatures far below freezing. We speak of bitter cold, of frostbite, of ice storms, yet even in these extremes there is no cold particle. Snow does not contain cold energy. Ice does not send cold. What happens is entirely about the loss of energy from living organisms and objects. The faster the energy leaves, the more acute the sensation of cold. The body responds with shivering, vasoconstriction, and other mechanisms to slow the loss of energy. Cold is the body's reaction to heat departure, not an external attack. Feynman also applied these principles to chemistry. Consider chemical reactions that occur at different temperatures. Reactions slow down in cold environments, not because cold inhibits them, but because molecules have less kinetic energy. Lower motion means fewer collisions, less interaction, and slower reaction rates. Once again, cold is an absence of energy, not a force acting on the molecules. Even thermometers, the tools we trust to measure temperature, reinforce Feynman's perspective. A thermometer does not measure cold. It measures the expansion or contraction of mercury or alcohol in response to molecular motion. It detects the presence or absence of energy, not an entity called cold. Temperature readings are always indirect measurements of motion. Cold is a concept we use to describe low energy. It is never measured as a substance itself. Feynman extended these ideas to biology. Animals in winter conserve heat, they hibernate, grow fur, or seek shelter. Plants survive frost by slowing metabolism. None of these survival strategies combat cold as an invader. They preserve energy, reduce heat loss, and manage the flow of energy to survive. Cold is never fought, heat is maintained. The universe operates in terms of energy and motion, not in terms of abstract coldness. The philosophical implications are as profound as the physical ones. Human language and intuition mislead us. We describe experiences as though cold were real. We panic in winter, fearing the chill. We take precautions, imagining an external force we must resist. Feynman's insight strips away the illusion. Cold is a story we tell ourselves, a subjective perception of heat loss. Reality is far simpler and more elegant. Energy flows, particles move, and everything else is interpretation. To bring this full circle, Feynman's proof lies not in a single experiment, but in the coherence of these principles across scales. From hands in ice to thermometers, from chemical reactions to the movement of molecules, every observation confirms the same truth. Cold is the absence of energy, not a substance. Even the most extreme, the most bitterly frigid, and the most terrifying winter conditions are simply the universe draining energy from one system to another. There is no enemy called cold, only motion, only heat, only the beautiful dance of particles obeying the laws of physics. Absolute zero and the final proof. We have arrived at the edge of our understanding. In parts 1 and 2, we explored Feynman's radical insight. Cold is not a substance, it is not an energy, it is not a force. It is merely the absence of heat, the retreat of energy from one system to another. Energy moves, particles vibrate, and what we perceive as cold is nothing more than energy leaving our bodies, objects, or the environment. But what happens at the extremes? Can we imagine a place so cold that cold itself exists? Can we touch absolute zero and prove that cold is real? Richard Feynman, ever the explorer of extremes, thought experiments, and quantum reality, provides the answer. Even at the limits of the universe, cold remains a concept, not a thing. Absolute zero, the theoretical temperature at which all molecular motion would stop, is the point at which we might imagine cold becomes real. 0 Kelvin, Mussy 73.156T, represents the complete absence of thermal energy, or at least the minimum possible under classical physics. For centuries, scientists speculated about what would happen if we could reach this limit. Would a person or object feel an attack of cold as though a substance had invaded their body? Could cold itself be harvested? Feynman's insight in modern physics reveals the truth absolute zero is a limit of motion, not a repository of cold. Even at temperatures approaching zero, quantum mechanics intervenes. Particles never stop moving completely. They exhibit zero-point energy, the residual, irreducible motion dictated by the uncertainty principle. In other words, even in the extreme stillness of absolute zero, there is no coldness to be found. Only motion remains, minimal though it may be. To understand this, we must examine the behavior of particles. At higher temperatures, molecules jostle, collide, and vibrate energetically. As energy is removed, motion slows. But quantum physics dictates that particles cannot have precisely zero energy, because doing so would violate fundamental principles. Even in a Bose-Einstein condensate, one of the coldest states of matter ever achieved, particles are not inert. They move collectively, obeying the laws of quantum mechanics. There is no substance called cold, there is only energy, motion, and the absence thereof. Feynman often emphasized that this is not abstract theory, it is measurable reality. Experiments with ultra-cold atoms confirm the presence of zero-point energy. At temperatures just billionths of a degree above absolute zero, atoms behave in strange counterintuitive ways. They form coherent quantum states, display wave-like behavior, and resist further cooling. No cold particles invade these systems. Heat simply cannot be extracted beyond the quantum limits. Cold, once again, is revealed as a human perception of missing energy, not a physical entity. This principle also resolves many everyday misconceptions. People often fear cold as if it were an active agent, frostbite, hypothermia, ice storms. Feynman reframed these experiences. Cold does not attack. You experience danger not from cold itself, but from your body losing energy faster than it can replace it. Your organs, muscles, and cells require energy to function. When energy departs rapidly, symptoms appear. Cold in every sense is a descriptor of energy loss, not an external invader. Even in extreme space environments, the same principle applies. Deep space is often described as cold, hovering just a few degrees above absolute zero. Astronauts feel nothing unusual until they begin losing heat from their bodies. Objects exposed to space slowly radiate energy. The universe does not send cold toward them. Cold is the absence of heat, the depletion of energy from a system, and nothing more. Feynman's radical insight also extends to how we manipulate temperatures in laboratories. Refrigeration, cryogenics, and ultra-cold physics all operate by removing energy. Engineers and scientists never add cold. They subtract heat, lower energy, and observe the effects. Cold, in every sense, is a human shorthand for describing these lower energy states. Thermometers measure motion. Not cold sensors detect energy flow, not a substance. Every device, every experiment reinforces the same conclusion. Cold does not exist independently. To bring this to its ultimate proof, consider entropy. The second law of thermodynamics tells us that energy spontaneously flows from regions of high to low concentration. Heat disperses. Systems seek equilibrium. There is no spontaneous generation of cold. Cold is not transferred, it is experienced as the lack of transferred energy. Whenever you perceive cold, it is because heat has left your body or object. There is no reverse mechanism in which cold invades a system. Energy flows, motion slows, perception arises. Cold is a narrative, not a reality. Feynman delighted in highlighting how misconceptions about cold pervade language, literature, and culture. We speak of cold winds, cold hearts, cold stares. Even metaphorically, cold is described as aggressive, active, and tangible. Yet physics shows the opposite. Cold is passive. It does nothing. It exists only as the absence of action, the retreat of energy. Nature has no need for cold. It needs only energy and motion. One of Feynman's favorite illustrations was snow. Snow feels cold, freezes your toes, and makes winter unbearable. Yet snow contains no cold. Its molecules are simply moving more slowly than ours. When we step on it barefoot, our energy flows outward, our particles slow, and our nervous system interprets the deficit as cold. The snow does nothing to us. Cold does not touch us. Heat leaves us, and that is all. Even in climate science, the same principle applies. Polar regions are called cold because temperatures are low, but the air molecules are still moving. Sunlight, seasonal cycles, and heat transfers govern climate. Cold is a human perception of heat deficiency, a way to communicate energy differences. The planet never generates cold as a force. It redistributes energy, creating gradients that our senses interpret. Feynman's ultimate proof, then, is both elegant and simple. Cold cannot exist because it is not a thing to exist. Everywhere we look, from daily experience to molecular dynamics, from thermometers to quantum states, from ice cubes to interstellar space, the evidence is consistent. Energy moves, motion changes, heat is lost or gained. Cold is a convenient term to describe energy absence, but it is never a substance, never a particle, never an active agent. It is purely perceptual. In conclusion, the universe contains heat, motion, and energy. It does not contain cold. Our perception of cold arises from the retreat of energy from one system to another. Feynman's insight dissolves centuries of misunderstanding. There is no invisible cold substance, no external force attacking us in winter, no cold to be trapped or transferred. Cold is a shadow, a story told by the absence of heat, a human interpretation of energy in motion. This understanding changes not only physics, but philosophy. It reminds us that human perception is fallible, that intuition can mislead, and that the universe is governed by principles far simpler and more elegant than folklore suggests. Cold is nothing. Heat is everything. Energy flows, particles move, and what we feel is only a reflection of motion, not an independent entity. Richard Feynman's proof is clear, beautiful, and unavoidable. Cold does not exist.